Hi, I'm going to talk a little bit here about the use of an array system for performing direction finding, a very common tool which is used by regulators and military and commercial entities for tracking sources of various transmitters. We're using the RFeye site software, which has a wonderful function to also act as a simulator. And what we have in this simulator, I have a number of elements which we've installed and will use. One of which is an array. We also have some transmitters out here in the countryside, and here on another B road we have another array sitting waiting for us to use. We're just going to use one array and one transmitter to begin with. Let me get that started. And this is typical of what a lot of manufacturers will show you when they're trying to demonstrate their direction finding equipment. So a signal with a very strong, clean signal, very low noise in the background. What the array is doing is commutating around the different antenna faces, looking into this frequency band, and of course therefore working out where the signal strength is at its strongest. So looking at the angle of arrival based on amplitude. And here, as you can see, we've got a nice strong stable bearing pointing out towards that transmitter. Nice and easy, but not at all representative of real life. Because in real life, the signals are not always strong CW signals, they may be pulsing. And of course, they're not always strong in terms of signal to noise. They could be co-located with other signals, there could be a lot of background noise around them, and it causes a lot of problems for direction finder equipments in real life. And this is something that CRFS, that we're very keen to educate and help our customers with, and to be able to show them some of the many tools that we've got available to help eliminate the issues that you see in real life. So let's start to try and show you a little bit of how real life looks. So first of all, what we'll do is with our simulated transmitter out here, let's actually turn that into a pulsed transmitter. So it switches off and on a 1 second cycle, as you can see in the simulator window here. And what you can see is when the signal is on, we get our nice strong stable bearing. But of course, when it's switched off, the algorithm is working against the noise in the background and this frequency slice, and of course it's just reading random rubbish. So that's a problem for a lot of customers who are looking for signals which are pulsing. You've got to be able to handle those guys. Let's make the situation a little bit worse. Let's now add a background signal. So what we have here is we have a broad background signal which I'm using as a noise source, but we still have our original pulsing signal flashing on and off the top. And what you can see with the direction finder now is when the signal, the strong signal, is on, we're of course providing a great direction find. But when it's switched off, of course it's direction finding against this noisy background signal, and of course it's pointing at the other guy. So for an inexperienced operator, the question becomes, what's really the signal of interest? And in real life, it's not even as simple as this, because the signals you could be hunting for are relatively small against the background noise. The background noise here is fairly stable in terms of its amplitude. That could be going up and down depending on what's happening in the ambient environment. So life gets pretty messy pretty quickly. The solution from CRFS is we've worked on our AoA processing, the angle of arrival processor that we use. And what we can do is we can start to add things like, I'll just add a couple here, and a squelch. So what we can start to do now, we'll draw your attention to this window at the bottom. What we're starting to do now is put some thresholds into place. And what we're saying here is we have a squelch below. So any signal which is below, and if I just move that up and down to show you it's moving live on the screen, we can actually put a threshold point in place and it will discard any data which is below this threshold level, so it will squelch that data out and it will only direction find against the signal that appears above. So as you can see now, I'm only squelching below that figure, so I'm not looking at the noise that's in the background, I'm only looking at the signal when it's here. You still see a little bit of movement on the bearing. The reason for that is the signal itself is pulsing off and on. And one thing we can do is actually change what we call the quench. And what that does with our software is when the signal is not visible, the analysis will actually stop. And what we'll keep is we'll keep the old bearing on the screen for, in this case, up to 5 seconds. So again, we can produce a nice stable bearing against that capability. Let's do what a lot of customers do right now, which is actually to use two arrays, because one array will give you a line of bearing. Two arrays will then, at the intersection of the two bearings, allow you to triangulate and give you, if I zoom in a little bit here on the map, oh, I missed it, I have to be quite precise. So it's coming in and actually giving us a geolocation at the intersection here. Let's just zoom back so we can see things here. And as you can see, the two bearings are intersecting, nice and stable, because both of the arrays are using the same mathematics and the same thresholds here. It's beautiful and stable. Let's back that off a bit to show you some of the frustration some direction finding users experience. And let's back off some of this processing and the squelching capability. And what you'll see now is some of the frustration that users of direction finder systems have, which is now it's looking in this frequency slice with no discrimination against noise to signal. And what it's doing, of course, is it's jumping around and it's giving a very big, broad heat map around the location of what we think is there. Let's click those back in again so it does the processing. And again, all we're doing now is just measuring against that pulsing signal only when it's present, and it gives a wonderful, stable geolocation using the arrays. So using two arrays is a great way of being able to do geolocation, but there's actually a third methodology as well. And this is one that we advocate very strongly. A lot of our users put our arrays into vehicles. And what we do is we use the same array, but we actually drive and move the array device. This is particularly useful in urban environments where reflections of the signal can actually cause distortion and confuse an array. If we actually manage to move the array and do cumulative measurements, what we do is we start to build up a series of lines of bearing from the same array overlaid on the same map. And what that does is by moving and moving and moving, we're able to anti-alias reflections and start then to really look into the true location of the transmitter we're looking for. So I'll give you a quick example of that here. What we'll do is on our geolocation, I'm actually using just one device. We're going to put the cumulative AoA capability on board. And what I'm going to do now is just pick this up on the map and simulate a vehicle driving around this A road that's here. And what you'll see is as we drive this device around, we're starting now to accumulate some of those line of bearings. And the system is calculating a heat map for geolocation based on the accumulation of those bearings. Let's move the vehicle again. Move, move, move. Let's bring them down and take them onto the A14. And what you can see, the accumulation of those bearings now is actually building that heat map for us, and we're able to geolocate with a very strong certainty. Let's take a look. 50% within a almost 50 meter by 50 meter square, exactly the location of that transmitter. So this sort of cumulated measurement capability that we have is very cost effective. It's using one array instead of multiple arrays. And also it's very smart because by moving the array around and doing this cumulative measurement, we're able to anti-alias out any reflections or spurious signals that we see and truly give a very accurate heat map sitting there, being able to define and discover where the transmitter is sitting. Okay, well, we hope that's a helpful little guide and insight to our array and direction finding capability. Don't hesitate to let us know if you'd like to have a real trial. Remember, we have a network of nodes in the Cambridge region. We also have some arrays available, and we're happy to give you a live hands-on demo at any time so you can get a little bit more insight to our amazing solutions. Thanks for your time.